Is
Yeah, that's what you're- yeah.
It is? But I think you did.
No, no.
What problem is this?
Number, Professor, it's number 4, right? Number 4. Yes.
Oh, then just flip it over.
Hey guys, mind if I distract you for a real quick second? So, I'm just gonna go over problem number 4 real quick. Problem number 4 is one of the more difficult ones. You're given an irreversible adiabatic expansion. And we know that when expansions happen adiabatically, that heat is lost, right? Because, or as long as it's not a free expansion, not heat, but energy is lost because work is done on the surroundings, right? And so your system is going to a lower energy state ultimately than it started at. Its volume is also increasing. So temperature is decreasing because it's spending energy while doing work on the surroundings. The volume is increasing because volume is increasing. And so what we have to do is we have to find reversible paths that get us from our initial temperature to our final temperature, our initial volume to our final volume. And we're going to do this in 2 steps. Now you can go double check the work. I didn't actually do the work, I just copied these guys. But they're telling me that if you calculate the final temperatures and final volumes for this adiabatic expansion, that you come out with a final temperature of 202.4 Kelvin. Again, check, or is it 202? Yeah, 202.4 Kelvin, and a final volume of 42.14 liters. It'd be good practice to run through that problem and verify that those are accurate for the sake of practicing those adiabatic expansions. So again, it's cooling, volume's increasing. We're going to calculate the entropy change along 2 paths, and we're going to pick convenient reversible paths. First, we notice that our volume goes to 42.14 liters from 12.4 liters. And so we're going to use the convenience of that isothermal reversible expansion to calculate delta S for the volume change. This is the one that we just did on the board earlier. Delta S is dq reversible over T. dq is work for an isothermal process, and the work is the integral of nRT over V dV. So we take nRT over V dV divided by T, the T's cancel. We're taking the integral of nR over V dV. We get natural log, nR times natural log of V final over V initial. So the entropy change for the first step should be nR natural log of 42.14 over 12.4, right? Now, we've found a path that takes us from our initial volume to our final volume at constant temperature, but our temperatures aren't right. Our temperature, we need to account for the decrease in temperature due to energy being spent as work. And so for that, we're going to hold our system constant at the 42.14 liter position, but we're going to cool it by draining energy out of it. So for this calculation, again, delta S is equal to dq reversible over T. We're going to use our constant volume heat capacity because, again, the volume of the system isn't changing. So figure out what CV is. I think it might mention CV for the thing in the problem. And we're taking the integral of CV dt, that's dq, CV dt is dq in this case, over T from initial to final temperature. Assuming that CV is not a function of temperature, it can be pulled out of the integral. And so now we're taking CV times the integral of dt over T. That's just CV natural log of T final over T initial. T final, they said, was 202.74, T initial was 298.15, and so this term is the delta S for that constant volume cooling path. So the actual change is from T1 V1 to T2 V2, but we calculate that change along a path that takes us to T1 V2, and then another path that takes us from T1 V2 to T2 V2, right? So there's 2 paths. This is delta S1, and this is delta S2. But the total delta S moving from one to the other is delta S1 plus delta S2.